The standard assumption in machine learning is that optimal neural network architectures require two things: full graph backpropagation and high-precision 32-bit floating-point arithmetic. To get these large models onto smaller devices, developers typically rely on quantization-aware training, or QAT. They use a heavy, high-precision shadow master during training to accumulate the tiny gradient updates before finally exporting a compressed, lower-resolution model for inference. Welvet AI Engine completely rejects this methodology. It enforces storage truth, forcing gradient descent to execute strictly within the native data type. The high-precision scratchpad is dropped entirely. The network computes its backwards pass strictly within those quantized mathematical bounds. Enforcing this uncompromising constraint isolates the true mechanical cost of low-precision neural computation. When we strip away this safety net of simulated precision, the standard results we expect from these networks begin to shift in ways that standard theory struggles to explain. This brings us to the Lucy benchmark, specifically the MHA Lucy Report 4 dataset. This dataset records the empirical performance of 2,346 distinct multi-head attention topologies, all tested on a localized associative recall task of matching query keys. Every single grid cell was evaluated under strict edge environment parameters, a minimum of 2,000 milliseconds, processing 1,024 training iterations, sampled by live 50-millisecond pulses. The results from these tests challenge the idea that high-precision math is a requirement for these types of bounded edge tasks. This central paradox of this dataset is found at the top of the leaderboard. A tiny 1-bit binary architecture perfectly matched a massive 32-bit floating-point network. Despite being constrained to binary weights, this tiny architecture achieved perfectly identical associative accuracy to the heavy Float32 champion. By maintaining parity and representation while shrinking the memory footprint by over 97%, this outcome forces us to investigate where our efficiency assumptions went wrong. A common architectural dogma dictates that multi-branch routing automatically improves a network's feature extraction capabilities. The baseline was a single topology, a linear stack of nodes with an unbroken path from input to output. This was compared against a Tricameral sandwich architecture, where the network bifurcates into independent hemispheres, forced to merge back together at the head. The empirical results showed that the Tricameral architectures suffered a massive 3.06x degradation in raw performance compared to the single linear stacks. This failure happens for two reasons. First, highly localized associative recall tasks require a highly cohesive representation space to map queries to their keys. When the data stream is routed through independent Tricameral branches, that continuous representation is physically fragmented. Second, the physical requirement to independently update disparate weight matrices and then merge their outputs at the head layer introduces lethal memory bandwidth latency. Topological complexity operates as a strict penalty in homogeneous associative tasks. Parallel routing must be justified by multimodality necessity, not deployed as a default heuristic. To understand how latency impacts these models, we have to look at this equation governing the Lucy score. A model's final score equals its throughput multiplied by its availability multiplied by its soft accuracy. When you look at the raw leaderboard, a mathematical anomaly emerges. The sparse family of training modes completely dominated the raw mean score. The sparse mode operates as a rotational duty clock. During any training sample, the head layer and one rotating hidden layer receive an update. Every other parameter receives a zero gradient update. By intentionally skipping most matrix multiplications, the network drastically reduces its workload. This shortcut inflates the availability uptime metric to nearly 50%, causing the final score to mathematically explode. But when you check the hard accuracy metric, the reality sets in. The sparse modes heavily trailed behind networks that computed full affine matrix walks. The sparse duty clock is highly optimal for keeping edge computing devices running continuously in ambient environments without triggering thermal throttling. But optimizing an architecture strictly for compute-to-inference ratios creates a mathematical illusion. It inflates hardware uptime while effectively masking severe degradation in actual feature extraction. If we discard the sparse duty clock anomalies, we can evaluate the true mathematical update protocols, specifically the head proxy and fast proxy training modes. Standard backpropagation operates by calculating cascaded Jacobians step-by-step backward down multiple layers, requiring the network to store intermediate data points for every single calculation. The proxy modes bypass this entirely, acting as optimized implementations of direct feedback alignment. Fast proxy computes the proxy gradient by bypassing intermediate activation derivatives, relying strictly on a transposed connection to directly feed the hidden layers. Out of the 2,346 distinct cells tested, head proxy running on a single linear architecture achieved the absolute peak individual raw score. This demonstrates that the output layer's transposed weight vector provides an optimal trajectory through the loss landscape, allowing hidden layers to rapidly align their representations. For stationary sequence matching, full backpropagation is completely redundant. Proxy gradients achieve alignment without the massive memory burden of storing intermediate activations. This brings us to the data types themselves. The dataset evaluated 34 native quantization formats, all operating under the strict conditions of storage truth. Predictably, the high dynamic range of 32-bit floats commanded the highest baseline scores across the grid. However, an extreme inversion occurred within the integer classes. Lower precision 8-bit integers drastically outperformed the wider 32-bit and 64-bit formats. To understand why, we have to look at hardware vectorization. A CPU processes data either through single processing lines or through packed multi-data pipelines. Modern single-instruction multiple data, or SIMD, factorization lanes are exceptionally efficient at packing these 8-bit integer dot products together. But wider 32-bit and 64-bit integers literally choke the AVX2 registers. They quarter the cache line efficiency and severely depress the overall throughput multiplier. Actual network performance on edge devices is dictated by physical silicon cache coherency and vector lane packing. It is not dictated by theoretical mathematical bit depth. Evaluating neural networks purely on raw score introduces a mathematical vulnerability. A model can achieve a massive score simply by being overwhelmingly fast, even if its actual learning capacity is entirely crippled. Dividing the score by the megabyte footprint to get a mobile score creates an even bigger trap, artificially elevating tiny, dysfunctional networks simply because their memory denominator is infinitesimal. To neutralize these vulnerabilities, the framework computes the Lucy-Pareto, or LPD metric. As this visualization shows, it enforces a strict quality gate. Networks must maintain a 70% geometric mean accuracy baseline against the board champion just to pass through to the next level. Once a model passes that 70% quality floor, it earns a shrinkage multiplier. This multiplier is based strictly on how much smaller its RAM footprint is compared to the overarching champion. The application of the LPD metric radicalizes the leaderboard. The heavy 32-bit floating point models are completely eradicated from the highest gold efficiency band. When strict accuracy baselines are combined with geometric memory penalties, standard high-precision architecture is entirely disqualified from the efficiency tier. Looking at this gold leaderboard, the top 16 positions are exclusively occupied by 1-bit binary architectures. The Apex champion utilizes a single sparse binary configuration, dropping its memory footprint from 2.0 down to just 0.1 kilobytes. This specific model maintained 94% of the Float 32 champion's quality while operating on a fraction of a single kilobyte of RAM. This performance gap reveals something specific about the underlying mathematical landscape, or the manifold the network has to navigate. In this associative recall task, that manifold is physically shallow. Because the landscape isn't complex or steep, the network doesn't need the infinitesimal precision of floating point numbers to find the right answer. It just needs the correct directional sign, the choice between a 1 or a 0. The reality of precision scaling is highly nonlinear. Chasing the final 5% of representational accuracy often requires a 3,000% increase in physical memory footprint. Neural optimization for bounded edge tasks must pivot away from the pursuit of unbounded accuracy. The true Pareto frontier belongs to asymmetric, single-stack, 1-bit architectures that rely strictly on proxy gradients.